Okay, so welcome to the 3 segments that will replace the live lectures. The first one is going to be about second order linear ODEs with constant coefficients. And in particular, we're going to look at the inhomogeneous problem. At this point, you should now see the vehicle that we're using to do these videoed lectures. This is the light board. Luke Skywalker has a lightsaber, we have a light board. All right, so what do I mean by these words? Well, we have a constant times the second derivative plus another constant times the first derivative plus constant times the function is equal to f of x. So now we've got something on the right-hand side. That was the homogeneous problem that we've already solved. Okay, so to solve this, we're going to use a recipe, and we'll elaborate a little bit more later on how it works. So here are the steps. I've got this particular problem. You find a solution to the problem without the right-hand side. That's the homogeneous problem. So I have a yh prime primed plus b yh prime plus cyh is 0. So that's the first thing I solve. Having done that, I then find a yp such that when I take that function and I pop it in here, instead of getting 0, I get f of x. And to do this, we will use educated guesswork. You'll see this also called the method of undetermined coefficients. But that's just really a highfalutin way of saying educated guesswork. Having found this and this, I then write a general solution for y, which is just yh plus yp. And then finally, if I'm given any initial or boundary conditions, I apply those. All right, so that's the recipe. There's 3 steps to it, right? And it's important to do it in this order. All right? So you find the homogeneous solution, you somehow make up a function that gives you the right-hand side. With those, you formulate a general solution, and then you put in any additional conditions, and at that point, you get a fully specified solution. At this stage, there are arbitrary constants. Okay, so that's the recipe, and let's just try it out on that problem, that ODE. I suppose we can also put in some initial condition. Let's do that. So we start with 0 for both y and the first derivative. Okay, so there it is. This is the recipe. This is an example. Let's just apply the recipe to solve it. Okay. Now, why does this recipe work? Whilst I'm erasing, let me give you a little bit of insight into that. So, the problem is linear, but there's something on the right-hand side. If there wasn't anything on the right-hand side, then I'd have this homogeneous problem, and when we solve the homogeneous problem, I convinced you that there were two solutions to this equation, and because it was linear and homogeneous, I could add them together to get a sort of more general solution. So now, for the inhomogeneous problem, there's something on the right-hand side, but if I can find a solution that gives you the right-hand side, that means that I can take that function and then add any of the homogeneous solutions, and it will still satisfy the same problem. So if I take these two equations and I add them together, I suddenly realize that the combo of yp plus yh satisfies the same differential equation again. Right? So that property of superposition still holds with yh plus yp, the homogeneous solution plus this thing, which people usually call the particular solution. So that's why it works. Let's see it in action. Okay. So, the one tricky thing at this point is going to be figuring out what yp is, the particular solution. And that's because, as I said, it involves educated guesswork. That's the method that we use in 256. Now, there are ways of finding this particular solution, yp, that don't use educated guesswork. It's a more formulaic approach. There's something called a Green's function. Variation of constants, reduction of order. Those are methods that allow you to figure out what the particular solution is without educated guesswork. But they're a little bit more complicated, and the types of differential equations that we'll deal with in 256 will be sufficiently simple that undetermined coefficients are going to really be the most expeditious way of finding the particular solution. Anyway, so let's apply the recipe to the example. There it is. So step one, find the homogeneous solutions. So yh prime prime plus yh is equal to 0 in this particular case. Instead of solving that, we solve an auxiliary quadratic equation, which is this one. That says that m is plus or minus I. M squared is minus 1. Okay, so this is the complex case. That means that I can choose yh to be either an a1 e to the ix plus an a2 e to the minus ix. That's a little bit ugly because it's got these complex exponentials. Or I can write something like c cosine of x plus d sine x. Right, the a1 and the a2 are arbitrary constants, the c and the d are arbitrary constants. And then there's that third way of writing it, which is r cosine of x plus some other constant. Right, so the big R and the theta there are constants, arbitrary constants. So I, most of the time, prefer this one. So we'll use that one here. Okay, so that's the homogeneous solution, step one. Now, this is the hard part, step two. I need a yp such that yp prime primed plus yp is equal to e to the x. Okay, so the way that it works with this educated guesswork, this method of undetermined coefficients, is you just look at what's on the right-hand side. And whatever you put in for yp, when you pop it in there and then pop it in there after differentiating, I've got to get that function. Right? So based upon what you know about derivatives, you need to pick a yp so that it's going to give you the right function. And then you add in some arbitrary constants in front, some parameters, so that when you feed it into this side, you can choose those parameters, those undetermined coefficients, so that you can actually get 1 times e to the x in this particular case. So you get precisely the right-hand side. Now, this is an exponential. When I differentiate exponentials, I still get exponentials. So clearly, here, if my yp, my particular solution, were something times e to the x, I would get something times e to the x there, something times e to the x there. So the combo here ought to be able to give me e to the x on the right-hand side. So I've just got to arrange whatever constant I put in front of the e to the x so that I get exactly 1 times e to the x there. That's how it works. So let's try it. I'll try yp is equal to some constant that I'm going to pick to make sure it works, and then I'm putting an e to the x in there because I know that gives me the right function when I differentiate it. So let's do it. Yp prime primed. Well, that's just the same thing. So this plus this, that's what's on the left-hand side. That gives me 2d e to the x has to equal e to the x. Well, there it is. The e to the x's are good. Just cancel them off. So I need 2d equals 1. So d is a half. So in other words, yp is equal to 1/2 e to the x. So that's the educated guesswork, right? I look at what's on the right-hand side. I guess, well, e to the x is going to be the bee's knees, whatever you would like to call it. I then feed it into the derivatives, assemble the left-hand side, make it equal to the right-hand side. I give myself the freedom of this parameter, this coefficient, choose it to get exactly what I need to get. And that's the particular solution. Step 3 is then to formulate the general solution, which comes from adding these two things together. So I'll put y is equal to, I'm going to use this one, so that's c cosine of x plus d sine of x plus the particular solution, 1/2 e to the x. So that's the general solution. Having done that, I need to then finally apply the initial conditions. So we'll do that next. At this point, if you are feeling a little bit nervous because you have to use educated guesswork, then worry not. In the lecture notes, you will discover that there is a helpful table. The way I've described it is that you look at what's on the right-hand side, you look at your inhomogeneous term, the f of x, and based upon what it is, you then make up a trial particular solution with the parameters in there, these coefficients that you pick to make sure it works. In the lecture notes, there is a helpful table that says, okay, well, if this is your right-hand side, these are suitable trial particular solutions. Once you've done it a few times, you get the hang of it. And it's not quite as worrisome as you might think to begin with. Okay, let's just apply the initial conditions here. So I put y is equal to 0 at x is equal to 0. So cosine of 0 is 1, sine of 0 is 0. So the first condition tells me that 0 is c plus 1/2. So c is equal to minus 1/2. Now, the next condition is on the derivative, so let's just differentiate this puppy. Differentiating a cosine, I get minus a sine. Differentiating a sine, I get plus a cosine. And differentiating that, I don't get the same thing. So now if I put x is equal to 0 again, to get y prime to 0, sine of 0 is 0, so I get d plus 1/2 is 0. So not only is c equal to minus 1/2, but so is d. So in other words, the solution of this particular problem is 1/2 e to the x minus cosine of x minus sine of x. Okay, so there it is. Let's just have a quick look at it and enjoy the methodology, the recipe that we just came up with. So what is it about? Well, it's about solving this equation with those initial conditions. So it's dead easy to just double check the initial conditions. So if I put x is equal to 0, I better get 0. If I put x is 0 in here, I get 1 minus 0, that's 0. And then if you go through the exercise of differentiating it, you can verify that. All right, so that's verifying the initial conditions here. That's all well and good. Now, if I take this, I should also check that it satisfies this equation. And if I take this, when I put either the sine or the cosine in there, this combo ensures that this function, when I put it in here, vanishes. And then when I put it in that one in there, it also vanishes. So these two are killed by that combination. When I put 1/2 e to the x in there, I get 1/2 e to the x plus 1/2 e to the x, which is indeed e to the x. So you see it in action, right? These are the homogeneous solutions. When you shove them in there, they disappear. This is this particular solution. When I shove it into there, I get the right-hand side as required. Right? That's often a useful exercise, double checking that your answer really satisfies both the differential equation and the additional constraints, the initial conditions here that you were given. Okay, so that's how it all works. Let's have another example that has a different function on the right-hand side, so we can kind of build up a repertoire of trying different particular solutions suited to what's on the right-hand side. Okay, so let's do a different example. At this point, I am not going to bother applying initial or boundary conditions anymore. There is one very important thing that you should remember, though, which is that when you go through the recipe, applying those additional constraints, it always has to be done last. You don't apply the initial or boundary conditions some part way through. You need both the particular solution and the homogeneous solutions in your general solution before you apply those conditions. Otherwise, you get the wrong answer. It's very tempting to try to calculate what the unknown coefficients are, the arbitrary constants in your homogeneous solution, without the particular solution. And that's the wrong thing to do. What you would find is exactly that had I done it that way around, so I would have applied the initial conditions without this piece, I would have got the wrong answer. In fact, I would have found that C and D was 0. And then when I assembled that homogeneous solution with a particular solution, it wouldn't have satisfied the actual solution that I've got at the end of the day. It wouldn't have satisfied the right initial conditions here. So it's important to keep the order. That's the only thing you must remember. Otherwise, the recipe can be applied, and the sticking point at the moment is figuring out precisely what your trial particular solution should be given what's on the right-hand side of the equation. So we'll have a quick look at some other examples to get a better feeling about that. Okay, so let's try y prime primed minus y is equal to, and then we'll do a bunch of different f of x's. Let's start with 3 e to the 2x. Okay, so the way that we're going to do that, we'll do this example, then we will replace that function with something else, and then with something else, and then with something else. So each time, the left-hand side will be the same. That means that the homogeneous solutions are always going to be the same. So in step 1, when I'm computing the homogeneous solutions, i.e. the solutions of this equation, I'm always going to get the same answer for all of the examples with different right-hand sides. Okay, so the auxiliary algebraic equation that goes along with this ODE is that one. That says that m squared is 1, m is plus or minus 1. So y homogeneous is going to be some arbitrary constant, e to the x, plus another one, e to the minus x. That's the homogeneous pair of solutions. Okay, we'll press on with the particular solution. Okay, so we've got an exponential here. It's e to the 2x. If I put e to the 2x in there, it's an e to the 2x, and then if I differentiate it twice, I get 4 times e to the 2x. Right? So if I try, my particular solution is some unknown coefficient that I must pick times e to the 2x. Feeding it into the right-hand side, I'm going to get the right functional form. Right, so this was the logic that we used last time. Let's just quickly do it. Plugging this in, I'm going to get 4 from bringing down the 2 twice with the 2 derivatives, times d e to the 2x, minus d e to the 2x. I've got to get 3 e to the 2x. So that's 4 minus 1, that's 3d. So clearly, the coefficients have been nicely chosen here so that you get d is equal to 1. So the general solution, 3, that's step 3, is to take these two things, add them together. I've got a1 e to the x plus a2 e to the minus x plus the particular solution, which is just e to the 2x. Oops. I'm writing a little bit too high up. There we go. That's better. Okay. So that was the first example. Let's go back and replace this with a new function now. And it'll be different. No longer an exponential. Let's try x squared. All right, step 1 is the same. So we don't need to do this again. And I'm going to keep the solution up there. I'm just going to replace this by what we get when we have now an x squared. So what's the educated guess in this case? So I need to put something in here so that when I leave it there or differentiate it twice, I have to get x squared. That's a quadratic. That's a polynomial of degree 2. Now, when I take a polynomial and differentiate it, I still get a polynomial. Right? You get rid of one of the powers of x, but it's still a polynomial. So if that was a polynomial, then this is still a polynomial, slightly different degree. But what I need to get is still a polynomial. So if you have a polynomial on the right-hand side, your educated guess would probably be that you should try a polynomial. So in this case, we'll try a polynomial. We need to get a polynomial of degree 2. So let's try a particular solution, which is a polynomial of degree 2. Here it is. Now, we'll discover that it's important to keep all of the terms in this polynomial in order to make sure things work. Right? The guiding principle when you do this educated guesswork method of undetermined coefficients is that you leave yourself enough freedom in here in order to arrange, when you plug the guess into the left-hand side, you arrange to get the right-hand side. That's the way it works. So that's why we're going to keep all three here, just to make sure everything works out. What I need is the second derivative of this, which is just 2d2. So let's take that minus that. I have to get x squared. And this is, at this stage, this is where I'm going to start picking the coefficients to make sure it works. So I've got polynomials on both sides, so let's just match up the coefficients of the different bits of the polynomial. So for example, what about the x squared terms? There's an x squared there, there's an x squared there. So minus d2 I would like to pick to get 1. Let's have a look at the x's. Okay, so in x I just have one term there. Minus d1 is 0. And then the constants, the bits that don't have any x's, I have a 2d2 minus d0 is equal to 0. Right, there are no x's or constants on that side of the equation. So I find that d2 is minus 1. This one tells me that d0 is twice d2. So it's minus 2. And this one just tells me that d1 is 0. Okay, so let's have a quick look. So we posed this thing. It turns out that to make sure it works, we need both the d0 and the d2. And those are the specific numbers that we need. It turned out that we didn't need the d1. You can sort of easily see why it turned out that we didn't need the d1 here. This is the original polynomial, which has got a quadratic, a constant, and a linear term. Right? There's no constants or linear terms on the right-hand side. On the left-hand side here, not only do we have minus the particular solution here, but we've got its second derivative. Now, when we differentiate a quadratic, we just get a constant. So there's a constant in there, and there's a polynomial there, and I've got to get x squared. So since there's no term in x on the right-hand side there, strictly speaking, you don't really need this part, because when it appears on the left-hand side there, there's nothing for it to equal on the right-hand side, so d1 is 0, as we found. But we did need the d0 and the d2 just to make sure it worked. So having done that, I can now write down the general solution. This is a homogeneous solution, and I've got minus 2. That's the d0, and minus x squared. That's the d2x squared. Okay, so there's the solution in this case. Right. So we've now done an exponential. On the right-hand side, the trial particular solution was an exponential. We then put a polynomial on the right-hand side. The trial particular solution is a polynomial. So the educated guesswork at this stage starts to look rather more transparent. You basically see what function is on the right-hand side, and then you make up a trial particular solution that looks very much like it. And the reason why it all works is simply because of what happens when you start differentiating that type of function. Okay. So let's try cosine of x. All right, so what do I need for my trial particular solution in this case? Well, when you take a cosine and you differentiate, you get a sine. Conversely, when you take a sine and you differentiate it, you get a cosine. Then when you differentiate that again, if you had a cosine to begin with, you get back a cosine with a minus sign. And similarly, if you differentiate a sine twice, you get back a sine. So that means that sines and cosines, when I start differentiating them, they stay as sines and cosines. Right, so what I need to feed into the left-hand side here is something that gives me a cosine. Well, clearly, the best, most general choice to ensure that things will work will be a combo of sines and cosines. So here it is. Let's try it. Let's do d1 cosine of x plus d2 sine of x. So this is going to be the general rule. If you see a sine or a cosine on the right-hand side, we'll try a sine and a cosine for the particular solution. So I need to differentiate it twice. In this case, since I have just cosine of x or sine of x, when I differentiate twice, I get back the same thing with a minus sign. Let's take this and plug it in. So I have this minus that. So I can do the algebra pretty quickly. That's what I get on the left-hand side. On the right, I have a cosine. So to make it all work, d1 I would like to be minus 1/2. That's going to replace this by 1. And then I don't have a sign on this side, so I should put d2 as 0. Okay? That means that my general solution for this problem is the homogeneous solution is minus 1/2 cosine of x. Now let me just put a note in here. Note. When I did this, it turned out that I didn't actually need the sign. That would not have been true if there had been a first derivative term in there. Right? If you think about it, the problem is when there's a first derivative on the left-hand side there, because one derivative turns a cosine into a sine and a sine into a cosine. So had there been a first derivative on the left-hand side there, it would have mixed up the sines and the cosines. So if the left-hand side had been y prime primed minus y primed minus y, what would have happened if I'd put this in there? I would have got minus d1 cosine minus d2 sine. That's in here. The first derivative, it would have been minus, and the first derivative would be, of this thing would be minus d1 sine plus d2 cosine. And then I've got the original thing there. And then let's say we still had that right-hand side, so I've got to get cosine from all of this. All right, so if I change this equation so that I have an extra term in there, this is what I would have got. And if I now pick off the coefficients so that I get the correct right-hand side, I've got to match up the cosines. So let's look at the cosines. I get minus d1, so there's a minus 2d1. That's the same thing as what we had over there. But there's another cosine here, which is this one. It's minus d2. So that has to be equal to 1. Now if I look at the sines, there's a minus d2, there's another minus d2. But there's a 1 from here, right? That's from this mix-up by the first derivative. So at this stage, I have these two simultaneous algebraic equations to solve for d1 and d2. And at this stage, it's pretty easy to see that both d1 and d2 are not 0. Right? So if there's a first derivative term, you definitely need both of them. That's something to bear in mind. So that's why the general entry in the table, right, the guiding table of educated guesses, which says if you have a sine or a cosine on the right-hand side, you try both as your particular solution. Okay, let's try another example. So far, you know, aside from this issue of one derivative turning a sine into a cosine or cosine into a sine, it's simply a question of staring at what your f of x function is, the right-hand side, and then essentially putting in a guess which is the same sort of function. That's how it's worked. So there's one instance where that can go wrong. So let's have a look at that. This will be when the right-hand side has a very specific form. Let's try it with this. So this is just an example, but it illustrates the point. What's unusual about this? It looks like an exponential. So, you know, the first type of example that we dealt with was an exponential. You just tried an exponential. It seemed to be pretty much the easiest case, actually. So what's unusual about this? Well, if I just proceed over here a second, this is my homogeneous solutions, and I'm just at the moment trying to figure out what to put in the space for the particular solution. Now, if I have a quick look, I suddenly realize that one of the homogeneous solutions is exactly what's on the right-hand side. Okay, so obviously that's a little bit special because, right, you get these two homogeneous solutions. Now we're putting one of them on the right-hand side there. Why would that cause a problem? Well, the educated guesswork that we've been using is to say, okay, well, I look at what's on the right-hand side. If it's an exponential, I try an exponential. So that means you would be tempted to try, your particular solution is some parameter that I'm going to fix times that exponential. Why is that a bad thing to do? Well, it's precisely because that's a homogeneous solution. The property of the homogeneous solution is that when you feed it into the left-hand side, you get 0. So if I feed this into the left-hand side, you can just do it immediately, I get the second derivative is just the same thing. Right? So that minus that is 0. So if you go through this educated guesswork at this point, I get that embarrassment. So clearly, something's gone wrong here. Let's just stop and think slightly more generally. Right? The general equation is the following. Right? It's a y prime primed plus by prime plus cy is equal to f of x. And here we've got a 2e to the x. But let's, for the sake of argument, just assume we've got some exponential, let's say alpha x, and then maybe there's some constant in there. Let's call that, we need a nice constant. How about a banana? It doesn't look much like a banana, but maybe you could think about it as a banana. So there's your banana. Okay, so we've got this equals a constant banana times that. So following this recipe, you would try yp is equal to some constant that we're going to pick, e to the alpha x. I take that, I put that into there, and if you just do the algebra, you get the following. There's my banana again. So at this stage, you say, woohoo, I'm on the right track because I can strike off the exponential. And as long as I pick d to be banana, it's kind of time consuming to draw bananas all the time. It's obviously not a good choice. As long as I pick d to be this, then I'm good. What could go wrong? Well, what could go wrong is if the denominator here is 0. If that was 0, then I would get an embarrassment like this. So this is embarrassing. No, I'm putting... It's embarrassing if a alpha squared plus b alpha plus c is 0. But that's just the auxiliary equation. So if alpha turns out to be one of the solutions of the auxiliary equation, one of the roots of that polynomial, we're in trouble. In other words, if alpha in here gives you a homogeneous solution, that's when this thing doesn't work. All right, so this is a general thing. If it turns out that the right-hand side is a homogeneous solution, you're in trouble. So how do we fix that up? Right, and we still need a particular solution in order to complete the recipe. What do you do? So if f of x, the right-hand side, is a homogeneous solution, try adding a factor of x to yp. We just add a factor of x. Okay? So this was the problem. This doesn't work. Right. If you'd have gone through this example and you hadn't observed that that was a homogeneous solution, you would have got to this embarrassment. You would have gone, oh, it would have been a Homer moment. So let's fix it up. So the guiding principle here is that if you have a homogeneous solution, it's not going to work when you put it in as a trial particular solution, but it might do if you add a factor of x. So let's try yp is equal to dx times e to the x. Let's try that. It's a bit more work to do all of the derivatives now because we've got a product. That's the first derivative. If I differentiate again, well, that just gives me d to the x. This is another product. When I differentiate that, I can differentiate there. That gives me another one of those. So I get that for the second derivative. If I come along now and I feed all of these into the equation, that's the second derivative. Now I need to subtract off the original thing. I need to get 2 e to the x at the end of the day here. You'll notice that there is this cancellation. You always get cancellations like that in this situation. It's like there was a cancellation that left the 0 there. When you put that into the left-hand side, there was a cancellation. Right? There's a similar cancellation there. However, having made that cancellation, you realize that after that I have 2d e to the x is e to the x. I can cancel off the times 2. I can cancel off the e to the x. So it'll work if I pick d is equal to 1. So this problem has the general solution of the homogeneous solution there plus x e to the x. Right? So there it is. That's the bit that corresponded to the homogeneous solution. The particular solution now is x times it. Right? So that's how you fix things up in that special situation. Okay. So at this point, we've now figured out how to solve the homogeneous problem and the inhomogeneous problem for second order constant coefficient linear ODEs. The recipe for the inhomogeneous case starts with the solution of the homogeneous case and then adds this particular solution part. And the general solution is the combo of the homogeneous and the particular solutions. And that's the end of the first segment.